So we'll pick up where we left off yesterday. So yesterday we had talked about the different types of sets of numbers. So again, that was natural numbers, integers, rational numbers, and real numbers were our four sets that we were concerned with here in this chapter. We're going to move on to SI units. SI units, that term should be familiar from science class, right? SI is like System International or whatever. It's the international system of measurements. So depending on the type of measurement you're making, there's a base unit, like a standard unit of measurement. So if you're talking about distance or length, your standard unit of measurement is the meter. Doesn't mean you have to measure things in meters, but that's the standard. Mass, the standard unit is kilogram, et cetera, et cetera. I have a bunch of these written down. For the most part, good morning. Hopefully we recognize most of these guys. Maybe with the exception of, light intensity or electrical current. But if you've taken like a big physics class, you probably even dealt with those. Probably did electrical and waves. To have seen those before. But there's not something you need to have memorized. It's just examples of what we mean by like a base unit. So temperature in particular, we have oftentimes three different scales in which we measure temperature: Fahrenheit, Celsius, and Kelvin. Often it's going to be necessary to convert in between these different temperatures. So we have three formulas here to do that conversion. To go from Kelvin to Celsius, we subtract 273.15 degrees. If you want to go from Kelvin or from Celsius to Kelvin, you'd add then. To convert from Celsius to Fahrenheit, you multiply that temperature by 9/5 and then add 32. Or to go from Fahrenheit back to Celsius, you would subtract 32 and then multiply by 5/9. Again, are these formulas something you need to memorize? Absolutely not. They'll be provided for you in any context where you need to use them. What you would need to know is like what the symbols mean in the formulas, right? Hopefully TC, TK, and TF, it's not hard to figure out which one means Celsius, Kelvin, and Fahrenheit. But that's the idea. The metric system is one of the preferred method of measurement in international math and science. One of the nice part about the metric system is that we can use a prefix to represent these base 10 multiples of a quantity. So if we talk about a millimeter, that's 10 to the negative third of a meter. So 0.001. Anybody with questions on the metric system? I think it's probably been covered to death in your science classes to this point. I'm just kind of like cruising through. You also have derived units. So a derived unit is like the product or quotient of two separate SI units. So if you talk about the area, that's the product of two lengths. So for example, meters squared. The volume is the product of three lengths, so like meters cubed. Velocity is the quotient of of distance and time. Acceleration is like the rate of change for velocity. So it's velocity divided by time again, so it's meters per second per second. Density is like the amount of mass per volume, per unit volume, so it's mass divided by volume. And notice here when we wrote the symbols, instead of writing meters divided by seconds, which is perfectly appropriate, more often than not in our textbook they typeset it with s to the -1 rather than doing m divided by s. I think because of typesetting issues, it's much easier to do a superscript than to put a fraction bar when you're typesetting a textbook. But either is fine, right? Division or negative exponent makes no never mind to me. So again, something I'm hoping is largely review is converting between two units. Probably did this extensively in your chemistry class. So if we want to say convert a linear unit, say from centimeters to inches, I know that 1 inch is 2.54 centimeters. So I make sure I line up my units on a diagonal. So like the top of this fraction and the bottom of this fraction both need to be in centimeters. And then we just kind of multiply across. And typically, unless otherwise instructed in an IB course, we'll round to 3 sig figs. We'll talk about what a significant figure is here in a moment. Now, usually for a linear conversion, most of us do this pretty well in our sleep, right? The place where we have to be a little bit careful if you're looking at a derived unit. So for example, if we have square units, so if we have an area, because this is centimeters squared, we have to do that same linear conversion twice. Because I technically have cm times cm in the bottom, or in the top, excuse me. To cancel it out, I need centimeters twice in the bottom. Alternatively, from a notation standpoint, like you could put a parenthesis around one of these factors and draw a squared out front. That would be fine also, but you have to remember to then use it twice. But if you're into that whole brevity thing, you're welcome to do that. I usually just write it out multiple times so I can't do something dumb and forget about my exponent. So if we're talking about a volume then, that's a cubic unit. How many times am I going to have to use that conversion factor? 3 times. So if it's 10 cubic centimeters, you multiply it by 1 over 2.54 3 times. Does everybody feel okay with this? Again, this will trip you up because you'll forget to do it. That's why I'm taking a moment, like giving you the numeric example and pausing here to really kind of hammer it. And you're like, Mr. Gluck, I get it. It's like, well, you say that now, but come quiz or test time, like at least a third of us are going to forget to do this, 2 times or 3 times or whatever you need to do. It's easy to forget. So I'm hoping if I say it like 3 or 4 times, it'll soak in a little bit better. All right. Questions on anything so far? Okay. So the next thing we're going to be talking about is like approximation and error. So when we talk about approximation in mathematics, really we're talking about how we're rounding. And now the thing to be concerned about in rounding is what level of accuracy is appropriate, right? So we round in the following way, depending on where we're doing that rounding at, which digit is being rounded. We look at the next digit to the right. If that digit is greater than 5 or greater, we round up. If it's less than 5, we round down, right? Standard way of rounding. You've rounded your entire life. No different now. Now, when we talk about where to do that rounding at, like which digit are we going to be rounding, this idea of significant figures becomes important. Now, from your science class, what is the purpose of using significant figures? Okay, that's okay. This is something that I think really helps you contextualize like why we're doing this. Yeah.
Is it to keep it all the same like decimal place?
It's not always to keep it the same decimal place. In fact, depending on what calculation you're doing, you shouldn't be using the same decimal place, which is hard, and why we think sig figs are hard. What makes it easier if we understand what is the purpose of doing this? It's not just to make things more complicated. So the purpose of the significant figure is it reflects the accuracy of your process, like how much accuracy you're able to do. So if I measure something, like I'm measuring some liquid, right? Say I have 5.17, liters of stuff. And then I split that into 3 batches. And I write down, okay, well, I had 5.17, and I split this into 3 batches. So I have 1.723 repeating in each batch, right? Now, if I write that down, that it somehow implies to the reader that the tool that I used to split that initial amount of liquid was accurate up to some absurdly small decimal point. And now, as a reader, I'm interested in what tool did you use to do this, because that is an absurd amount of precision with that tool, right? If all I did was measure this out with the same tool I used to measure the 5.17, I should not be able to say it's more accurate than 2 decimal places, than the hundredths place, right? So when I do a calculation involving a measurement, it's important that I'm not implying that I have more accuracy than my initial measurement than it had, right? Like somehow, like splitting this up, I could not have gotten a more accurate measurement of volume than I had initially. That shouldn't be the case. That's what the significant figures are doing, is it communicates to the reader the level of precision that you made that measurement with. Does that help contextualize like what these sig figs are trying to do, like why they're important? And the good rule of thumb is that doing a calculation should not create something that's more accurate than you had to start. Right? If you kind of think about that as your underlying rule of what the significant figures are trying to do, that really helps. So if you add like something that was 10, 5.7, and then 3.145, well, the least accurate measurement you made was the 10 that had one significant figure, right? You add those 3 things together, should be rounding to that 10 spot. Does that kind of make sense? So that's the idea. All right, let's continue on with this. Do I press this one? Great. Okay. So when we talk about significant figures, in this class, typically we're just going to ask for either an exact answer. So if you can write something as a terminating decimal, or as a fraction, or like 2√3 or something like that, that's always fine. Exact answer will always be fine. If you do any rounding, you should round to 3 sig figs unless otherwise stated. So the problem might say, give your answer to 4 sig figs or 7 sig figs or something like that. Then do that. If it doesn't tell you, you can give an exact answer or round it to 3 sig figs is fine. So let's talk about what we mean by significant figure, because this is going to be, we're not doing any measurements here. We're not actually working with instruments. We're not measuring volumes or using rulers or anything like that here. This is purely abstract. So let's just talk about significant figures in general, in terms that probably you remember from your science class. So any non-zero number, always significant, right? 1, 2, 3, 5, all of those digits, always a significant figure. The question is the zeros, right? So a leading zero is never going to be significant. A trailing zero is only significant if there's a decimal point. Right? So 23.00 implies that what I used to or 123.00, what that implies is the measurement tool I used was accurate to the hundredths place, and I could measure it as 23.00 or 123.00, as opposed to 123, which implies that the tool I used to measure that was accurate to the ones place. Tells me I used a different kind of instrument. Is everybody does this help kind of contextualize like why we're doing this, why this stuff, why there's a difference? Now mathematically, 123.00 and 123 are the same number, right? There's no difference in the number. It's what that number is communicating in terms of how did I get that number, like the tool I used. That's the difference. So if there's no decimal point, if it's just 10, that's 1 sig fig. If it's 10 decimal point, that's 2. If it was 10 decimal point 0, that's 3. Okay, the zeros at the trailing zeros are only significant if there's a decimal point. Everybody's cool? And then, okay, so again, not significant, there's no decimal point. And then sandwiched zeros are always significant. So if you're between like 1, 0, 0, 0, 0, 1, and all those zeros in between the 2 sig figs, or 2 significant digits, are always significant. Ouch. Does everybody feel comfortable with this? And again, in this class, we're never going to do any rounding on intermediate steps. So if we're doing a calculation that involves like, okay, I took this, I divided it by 3, and then I added 5.6 to it, and then I multiplied by 7.9, the only answer you should be rounding is the final answer. All the work in your calculator should be hanging on to all your digits and just rounding the final answer. Is everybody okay with that? So in a science course where there's measurements, you would be potentially rounding intermediate steps. We're never going to do that in this course. The only answer that requires rounding is the final answer. Everybody's cool? Okay. And again, not in the science department, I don't know how picky they are about how you're doing this, but I want to be real clear at what the expectation is here. And again, only round the final answer, no rounding on those intermediate steps. So it will be really important that when you're doing your work on your calculator, you're just doing it, like progressively, use your previous answer to do the next calculation or do it all in one line. And not like, okay, round this number, and then I'm going to type in, I got 5.17321, round that to 3 sig figs, and then do my next step. No. You got to keep the whole thing, all the decimals, along for the ride. All right. So when we do any kind of rounding, what there inherently is on that number is there's a margin of error. So if I take, say, the number 10 that was rounded to 1 sig fig, that number could have been as high as like 14.9 repeating, right? and could be as low as like 9.5, right? If we're rounding to 1 sig fig, both of those two things could be, have a big range of values there, right? That's what we're talking about when we talk about a bound on a number, is like, okay, this was a rounded number. How big could it have possibly been, and how small could it have possibly been? That each one would round to our answer. So again, if we take, say, the number 5, and if we round it to 1 sig fig, that number 5 could have been as big as 5.5 and as small as 4.5. Or I'm sorry, we should be just under 5.5, so like 4.9 repeating. Is everybody okay there with this idea? Okay. So when we're talking about a bound for a number, we're talking about like what was the smallest number that would round up to this, and what's the biggest number that would round down to it. So here, the way we could write that bound, we could say that our measurement could have been, or had to have been, greater than or equal to 4.5, but strictly less than 5.5. Does everybody feel okay there? And you'll always have a bound when you write your bounds that's, has an or equal to inequality on one end and a strict inequality on the other end. But it could be reversed, right? The strict inequality could be on the left end, and the greater than or equal could be on the right end if you have a negative number. Henry's looking at me like, how's that going to work? It's if you had a negative. Yep. They could be flipped. But in general, that's the idea. Does that feel okay? Could you write this using interval notation as well if you wanted to? Sure. Can you write an inequality? Yes. Should you do whatever is comfortable for you? Yes. Yep, so note the different signs. Okay. All right. So again, bounds can change depending on the precision of our measurement. So if we're rounding, we take 5 and we're talking about precise to the nearest 10th, means like we're rounding to the 10th place. So 5, we don't want to think about as 5. We want to think about it as 5.0, right? So the digit that we would have been looking to round to the 10th place would be the hundredths place, right? The second decimal point. So rounding up to 5, the smallest you could have been is like 4.95. And rounding down to 5, the biggest you could be is just under 505. Does everybody see this is still the same problem, right? I've changed the wording, but it's the exact same idea. Just presenting it in a different way so that when you're looking at your homework and you hear a different presentation, you're not confused. It's still the same problem. And it's just about being careful and making sure you are really reading and understanding what it's asking for, right? But it's not complicated. We're not doing any difficult calculation here at all. But you do need to you need to know the vocabulary, right? Like, what is this direction asking you to do? Yes, sir.
It's saying that the biggest number you could have, it's still round to 5 is 5.05.
Oh, well, it's less than 5.05. So it doesn't include 505. It's the first number less than that. So like 5.049 repeating. Is that?
Yeah.
Okay. All right. Again, hopefully this looks familiar from your science class. So when you make a measurement, right, you perhaps have a known value, like, hey, you know, like you do a chemistry experiment. It's like, hey, I'm trying to figure out how much, you know, acetaminophen is in this tablet of aspirin. Well, I know from the label on the box it says there's 150 milligrams, right? I do some titration and try to figure out how much is actually in there, like doing a scientific experiment. And I get, I calculated 148.6 milligrams. What was the error in my calculation? Well, that error is going to be the experimental value, or the approximate value, the one that I got from doing the process, minus the expected value, the known value, the value on the label of my medicine tablet, divided by the known value. Do the absolute value in case, like in my example, I had 148 minus 150, and then times by 100 to turn into a percentage. And that's giving you a percent error. So it tells you how close is your approximation to the actual value. Okay, the thing to remember is that the E isn't experiment or estimate. The E is the exact. Most common mistake students will make is just putting the numbers in the wrong spot in the formula. Again, do you need to memorize this formula? No. Formulas will always be given to you. All right. So that was section 1. Let's look at section 2. In section 2, it's just some review of some basic algebra rules, which is okay, right? So we're going to start by talking about exponents here. So recall a general exponential function is just something that could be written in the form a times b to the x, where a is some non-zero real number and b is also a real number that's non-zero, is greater than 0 but not equal to 1. Right? Why do we have these requirements on a and b? Well, if a is 0, this whole thing is just 0. That's a linear function or a constant function. That's not exponential. We don't want that. If b is 0, then the whole thing is 0. We don't want that. If b is 1, then b to the x is just 1. So that just turns into a. That's constant. We don't want that. And if b is negative, well, x can be any value. Specifically, it could be like a fraction with an even denominator, like 1/2. I know the exponent of 1/2 is the same as a square root. Now you're getting like undefined or imaginary results all over the place, like infinitely many of them. And the thing is like has infinitely many discontinuities, and that's just an incredible nightmare, and it's not at all what we want. So that's why we have those restrictions on a and b. It's just to make sure that what we're looking at is an exponential function that, you know, looks like we want it to.
Can b be greater than 1?
Yes, absolutely, but not equal to. Could be less than 1 also. Could be like 0.5, right? But it has to be greater than 0 and not equal to 1. That a coefficient we often refer to as the initial value. because when x is 0, b to the 0 is 1. A times 1 is just a. Oftentimes when we talk about these exponential functions, the x variable is representing time, right? When we talk about the initial value, that's when time is equal to 0. And in the exponential function, when x is 0, the function evaluates to a. So we call it the initial value. We call b the base. And basically that's the common ratio of increase. As x increases by 1 unit, f of x will increase by a factor of b. Well, I should change by a factor of b. I guess it could get smaller, right, if b is less than 1. And we say the end behavior for our exponential function so our function approaches 0 as x approaches negative infinity. So if you think about that, if we put a very large negative number up here in the exponent, the negative is going to make it a fraction, right? So it's like a divided by some fraction. If that fraction is getting very, very big in the denominator, what's happening to the value of the fraction as a whole? It's going to 0, right? If I take 1/2 and then I look at 1/3 and 1/4, each time the decimal is getting closer and closer and closer to 0. That's all that's happening here. It doesn't matter if the numerator is positive or negative. It does not. It still goes to 0. It just from above or below. So what that tells us is that we have a horizontal asymptote for all exponential functions of the form a times b to the x at y equals 0. Right, so I think we used the limit notation to describe end behaviors. I know we did that last year in my trig and pre-calc class. AP trigger or pre-calcers, you guys used limits to describe end behaviors last year. Does that notation look familiar? Yeah, okay. I just want to double check. If it's something you hadn't seen before, that's a different discussion, but I was quite sure that it was something that would have been done in that class. That's a new one that I haven't taught before. That's why I'm checking. All right. So again, when evaluating an exponential function, again, you have to remember order of operations, that exponents come before multiplication. So we have to take care of that power of x first and then multiply by a. So if you want, if it's easier to think about it as like a second set of parentheses there to really imply that, explicitly imply that order of operations, you can do that. So we ask the value of the function, f of x equals 3 times 2 to the x when x is 2. Who can do that? Henry? 2 squared is? There you go. And then times 3 is 12. Perfect. You can do that in your head.
No, this is easy. Oh, okay,
Yeah. I know. It's still like 8:22, so you're excused if like your mental math is not all firing on all cylinders. That's okay. All right. What if x is 0? Excellent. Yeah, that's just the initial value. Okay. And again, these exponent rules, like 2 to the 0 is always 1. We'll review those here in a moment. All right, negative 3.
3/8.
3/8, very good. So remember that the negative exponent makes a fraction.
How did you do that? Yeah.
2 to the third is 8, and then 3 times 1/8 is 3/8.
Wow, that was just.
That's correct also.
That's fine.
So remember, a fractional exponent is the same as a radical. Specifically, 1/2 is the same thing as a square root. So this is just 3 square roots of 2. Again, in a test setting, you could write that rounded to 3 sig figs if it didn't ask for an exact answer specifically, or you could leave it as 3 square root 2. Either would be fine. Could you write down the exact answer or an exact decimal for this? No way, Jose. Square root 2 is an irrational number, non-repeating, non-terminating. Good luck on that. You can be there a long time trying to write down that whole decimal. All right. Ooh, scary. Yeah, close. There's still some simplifying we could still do on that, but okay. So we plug in the negative 3/2. Let's do the negative exponent to make it a fraction. We'll separate this 3/2 into 3 times 1/2. So we'll do the power of 3 first. Then I know 1/2 is a square root. Oops. And I can simplify the square root of 8, right? That's square root of 4 times square root of 2. So we can make that 2 root 2. And then I'd have to rationalize that denominator. So it'd be 3 root 2 over 4 as our best answer there. You were correct. You just weren't all the way done with the simplifying, but that was great job. I don't know that anybody's going to do that all the way to there in their head.
I did it.
So you did, Allie.
Yeah.
You should have shared up with us and shown off. Been like, I got this, guys. Stand back. Yeah, I know. It's like your volleyball serves, right?
No, yeah, every time they go in.
Like, get out of my way. I got this, guys.
Absolutely.
All right. So some basic properties of exponents as promised. Let's review these again. We hit a lot of them there. So when I multiply 2 exponentials with the same base, the base stays the same and we add the exponents. When I divide 2 exponentials with the same base, the base stays the same. We subtract the exponent. That's assuming that a is not.
Oh, wow.
What value can a not have here? Or else it gets us into big, big trouble. 0, very good, right? Because 0 divided by 0 is, well, it's not 0. Yeah, it's indeterminate is the proper term for that. Undefined is fine, though. If you're ever curious, ask Siri what 0 divided by 0 is. It's quite humorous. So if I have the product of 2 numbers raised to a power, that exponent applies to both factors. So ab to the m becomes a to the m times b to the m. Similarly, in a fraction, if I have a fraction to a power, that power applies to the numerator and the denominator. Again, assuming that the b is not. What value can't b have? 0, right? This isn't true if b is 0.
Wow, that's fun.
Right down the middle.
All right. Negative exponent makes a reciprocal, right? We remember that. We just talked about it. If I have the exponent of an exponent, that's multiplication. I used that just a moment ago when I split the 3/2 into 3 times 1/2 in that previous problem. And then the fractional exponent gives you a radical. So the denominator of the fraction tells you the index for the radical. Everybody's cool? Remember these? And then more generally, if I have like a non-unit fraction, the numerator becomes the exponent and the denominator becomes the index for the radical. And then good old a to the 0 equals 1, assuming that a is not 0, right? If a is 0, that's indeterminate also. 0 to the 0 is not 1. It's not 0. It's indeterminate. So, if we wanted to solve an exponential equation, to solve an equation, typically we would apply the order of operations in reverse, right? So the first thing I'd want to do is undo any addition or subtraction. I don't see any. Next thing I'd want to do is undo any multiplication or division. I see that I have a times 20 out front. So to undo that, I'll start by divide both sides by 20. And now, to solve this, I could go one of 2 routes. I can choose to use a logarithm, and I can do the log of both sides. What base would I want to choose for the base of my logarithm to make this problem as simple as possible? Not 2, not 4. I'd use 1/2. I'd want the base of my logarithm to match the base of my exponential. Now, if you remembered logarithms, have at it, no big deal. If you didn't remember logarithms, the other approach we can take to this problem is we can try to make the bases of the 2 sides match. So I could rewrite 1/4 as 1/2 squared. So both bases match. Then I can just say, okay, well, if this exponent then has to equal this exponent. And then I multiply both sides by 6 or by 3 and I'm get my answer. Now, this is nice and simple, but it's not always possible, right? The logarithm, always possible, not quite as simple. So it's just a matter of preference there as to like which route you want it to go. Either would be appropriate. Both is fine. Both are correct. The other option to solve a problem like this that you can always use as well would involve your calculator. How could you do this with your calculator? I put this into y1, put this into y2, graph and find the intersection, right? If you still need to take, or if you're going to be taking another ACT in the future, that's an excellent, like, I don't know how to solve this. Doesn't matter, just put it in your calculator, left-hand side, right-hand side, find the intersection, done. You know, it's a multiple choice test, the right answer's there. All right. And, oh, yeah. For when we're solving exponential equations, no, we can't get it anyways. You can check your answer by just plugging things back in, but you see that that also does work. Right? That's it for section 1-2. That's all I really wanted to cover today. So if you look at the My Notre Dame, I have that's awful small. The schedule for the week is now up and posted. Today is Wednesday. I'll get that in as an assignment into the grade book here. Probably next period, I'll have a minute to get that in there. So for your homework submission, right? Remember, homeworks are going to be turned into your shared OneNote. On Friday, remind me first thing, and we'll go over kind of the different ways that you can do that. I figure I'll wait till Friday in case you have like I have the thing complete and I'm ready to just do it and take care of it. Again, you can write on paper. You can do your assignment on paper. You can do your assignment actually with the stylus on your tablet. Either is fine with me. Whatever your preference is, whatever you like to do that. And then if we need to practice getting into OneNote from paper, we'll do that on Friday. Does anybody have a syllabus sign-in sheet that they want to get rid of? If you don't, no big deal. I'm just reminding you because I'm the kind of person like, if I have it and I don't get rid of it, it disappears on me. So. Thanks, my dude.